Welcome to Cambridge IGCSE Physics, Lesson 56.1, Defining Half-Life. Today we explore radioactive decay and learn to define half-life precisely. This is core content for your examination. Half-life is a fundamental concept in nuclear physics that describes how unstable atomic nuclei decay over time. Understanding this concept is essential for applications in medicine, archaeology, and nuclear technology. We'll learn the definition, understand what it means physically, and practice calculations. This knowledge forms the foundation for more advanced nuclear physics topics. Let's examine our learning objectives for today. By the end of this lesson, you'll be able to, first, define half-life of radioactive isotope. This means you'll understand the precise scientific definition and can state it clearly. Second, know as time for half nuclei to decay. You'll understand that half-life represents a specific time period during which exactly half of the original radioactive nuclei undergo decay. Third, use definition in simple calculations. You'll apply the half-life concept to solve numerical problems. These objectives align with Assessment Objective 1, which focuses on scientific knowledge and understanding. This forms 50% of your examination marks. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, half-life, which means the time required for exactly half of the radioactive nuclei in a sample to undergo decay. This is measured in units of time such as seconds, minutes, years, or even millions of years. Second, radioactive decay, which means the spontaneous breakdown of unstable atomic nuclei, releasing radiation and transforming into different elements. This process cannot be controlled or stopped. Third, isotope, which means atoms of the same element that have identical numbers of protons but different numbers of neutrons in their nuclei. Understanding these terms precisely is crucial for mastering nuclear physics concepts. Let's explore our first core concept. What is half-life? The fundamental definition states that half-life is the time taken for exactly half the nuclei in a radioactive sample to decay. This means if you start with 1,000 radioactive nuclei, after one half-life period, exactly 500 will remain unchanged. The key points are, first, it's always exactly half the nuclei, not approximately half. Second, the time period is constant for each specific isotope. Carbon-14 always has the same half-life. Third, it's independent of sample size. Whether you have 1,000,000 nuclei or just 10, the half-life time remains identical. We use the symbol T sub 1/2. The diagram illustrates this perfectly, showing how a sample of 1,000 nuclei reduces to 500 after one half-life, then to 250 after two half-lives, and so on. Now we examine half-life properties. Understanding these characteristics is crucial. First, it's a random process. We cannot predict when any individual nucleus will decay. It might happen in the next second or in 1,000,000 years. Second, it's statistical. While individual decay is unpredictable, large numbers of nuclei follow predictable patterns. Third, decay follows an exponential pattern. The graph shows this clearly. Each half-life period reduces the remaining nuclei by exactly half. Fourth, each isotope has a unique half-life. Carbon-14 has a half-life of 5,730 years, while uranium-238 has 4.5 billion years. The range varies enormously, from microseconds for some artificial isotopes to billions of years for naturally occurring ones. The blue line shows actual data points, while the red dashed line shows the theoretical exponential curve. Let's work through our first example. The problem states, a radioactive sample contains 800 nuclei. The half-life is 10 minutes. How many nuclei remain after 30 minutes? We are given initial nuclei equals 800, half-life equals 10 minutes, and time equals 30 minutes. We need to find the number of nuclei remaining. Step 1. Calculate the number of half-lives. We divide 30 minutes by 10 minutes, giving us 3 half-lives. Step 2. Apply half-life reduction. After each half-life period, the number of nuclei divides by 2. Step 3. After the first half-life, 800 divided by 2 equals 400 nuclei. Step 4. After the second half-life, 400 divided by 2 equals 200 nuclei. Step 5. After the third half-life, 200 divided by 2 equals 100 nuclei. The answer is 100 nuclei remain after 30 minutes. Example 2 applies the same principle differently. The problem is, a sample starts with 1,200 nuclei. After 15 hours, only 150 nuclei remain. Find the half-life. Now we analyze systematically. First, find the reduction factor. We divide the initial amount by the final amount. 1200 divided by 150 equals 8. Second, express 8 as powers of 2. 8 equals 2 to the power of 3, meaning 2 times 2 times 2. Third, this tells us that 3 half-lives occurred during the 15-hour period. Fourth, calculate the half-life by dividing total time by number of half-lives. 15 hours divided by 3 equals 5 hours. The diagram shows this visually. Starting with 1200 nuclei, after 5 hours we have 600, after 10 hours we have 300, and after 15 hours we have 150 nuclei. Mathematical skills are crucial for half-life calculations. Let's examine 3 essential methods. First, step-by-step division. For each half-life period, divide the remaining nuclei by 2. Starting with 1000 nuclei, after 1 half-life, we have 500. After 2 half-lives, we have 250. After 3 half-lives, we have 125 nuclei. This method works well for small numbers of half-lives. Second, the formula approach. We use n equals n naught times 1/2 to the power of n, where n naught represents initial nuclei, n represents final nuclei, and n represents the number of half-lives. This method is efficient for larger numbers. Third, finding half-life when given initial and final amounts. Calculate the reduction factor by dividing initial by final nuclei. Express this as a power of 2 to find n. Then divide total time by n to get the half-life period. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a sample has 400 nuclei with a half-life of 6 hours. How many nuclei remain after 18 hours? This tests your ability to calculate the number of half-lives and apply step-by-step division. Question 2 is intermediate level. It states 2000 nuclei reduced to 250 nuclei in 24 minutes. Find the half-life. This requires you to work backwards from the given information. Question 3 is advanced level. The question is, after 3 half-lives, 75 nuclei remain. Find the initial number. This tests your understanding of the reverse calculation process. For all questions, remember to show you're working clearly, include appropriate units in every step, and check that your answers make physical sense. Attempt these problems now before looking at the solutions. Half-life principles power many real-world applications. Let's see how today's concepts apply in practice. In medicine, radioactive tracers use known half-lives for diagnosis and treatment. Doctors inject patients with radioactive isotopes that have specific half-lives, allowing them to track biological processes and treat diseases like cancer. The half-life determines how long the isotope remains active in the body. In archaeology, carbon-14 dating relies entirely on half-life calculations. Carbon-14 has a half-life of 5,730 years, allowing archaeologists to determine the age of organic artifacts up to 50,000 years old. In nuclear power, understanding fuel decay rates helps engineers calculate reactor efficiency and waste management requirements. Career-wise, this knowledge leads to specialized professions. Nuclear medicine technologists operate imaging equipment, medical physicists design treatment protocols, and nuclear engineers manage power plant operations. Let's review the solutions systematically. For question 1, we calculate 18 hours divided by 6 hours equals 3 half-lives. Then we apply step-by-step division. 400 nuclei becomes 200 after 1 half-life, then 100 after 2 half-lives, finally 50 nuclei after 3 half-lives. For question 2, we find the reduction factor. 2000 divided by 250 equals 8. Since 8 equals 2 to the power of 3, 3 half-lives occurred. Therefore, half-life equals 24 minutes divided by 3, which is 8 minutes. For question 3, we use the formula. After 3 half-lives, the remaining nuclei equal initial nuclei times 1/2 cubed. Since 75 nuclei remain, the initial number was 75 times 8, which equals 600 nuclei. Exam success requires showing all working steps, stating the half-life definition precisely as time for half the nuclei to decay, checking that numerical answers are reasonable, and using correct units throughout your calculations. Let's summarize today's lesson comprehensively. The key points to remember are, first, the definition. Half-life is the time required for exactly half the radioactive nuclei in a sample to decay. This definition must be stated precisely in examinations. Second, the properties. Half-life represents a random process for individual nuclei but follows predictable exponential patterns for large samples. Each isotope has its own unique half-life value. Third, the calculations. For each half-life period that passes, divide the remaining nuclei by 2. This simple rule solves most half-life problems. For further study, practice additional half-life calculations with different time periods and sample sizes. Review exponential decay graphs to understand the mathematical relationship visually. Prepare for more advanced topics, including radioactive decay equations and activity calculations. These concepts build systematically, so ensure you master half-life definitions and calculations before progressing to more complex nuclear physics topics.